Okay, so let's say that you're working on homework question number 7, and homework question number 7 requires you to use theorem 1.4.5 from your book. So theorem 1.4.5 from your book is quite the theorem. So let's say y is a unique solution to the initial value problem, y prime is some differential equation, some initial value problem, y of a equals alpha. So you're working in an interval from a to b, and f is continuous, and then there's this constant L such that this is true. Now, if you think about this equation, this inequality right here, if you were to divide both sides by the y1 minus y2, move that over, then you'd have like a rise over run. And so L is like a bound on your slope. So L is the absolute value, the max absolute value of the slope on that interval. And then you got capital M down here. Capital M is a bound on the curvature of your function. So if you have, if on your interval, your function, the slope is bounded by L, the absolute value of the slope is bounded by L, and the absolute value of the curvature is bounded by M, then you can have a bound. Then you know that your error is within a certain amount based on some fancy, in a lot of ways, I could explain this better if I knew that all of you had taken real analysis, but instead, we'll just use the theorem and on faith. All right, so the theorem tells us that we can bound our error by this formula right here, where these brackets are really like parentheses, so they're not absolute values there, because your TI will always be greater than A, and L is always positive, so e to a positive number is greater than 1, so minus 1 will be positive. So there's no need to absolute value there. Okay, so let's say you're working on number 7, which is way down here. Where am I? We're at important lessons, exercises. Okay, so in number 7, you're given this differential equation. I'm going to do a similar one, maybe do a different differential equation. So let's say I'm doing the differential equation, dy over dt equals 2y plus 1. Well, first I find the exact solution. So then we've got dy over 2y plus 1 equals dt. Integrate both sides, and you're left with natural log. I'm doing u substitution here. So u substitution, u is 2y plus 1. So I've got the 1/2, I think, out here. Yep. Natural log of 2y plus 1 equals t plus c. And then e to the power of both sides gives me, oh, but I can't simplify that yet. I gotta move the 1/2 inside. So e to the natural log of the square root of 2y plus 1 equals c e to the t. Moving, of course, the standard trick with an unknown constant is that e to addition and exponent is multiplication on the outside, and then just call it a new constant, capital C. So then I have the square root of 2y plus 1 equals c e to the t. So then square both sides. So then 2y plus 1 equals, well, c squared is just a new unknown constant, e to the 2t, and then subtract 1, c e to the 2t minus 1, and then divide by 2. Y equals, then divided by 2 is just a new constant, e to the 2t minus 1/2. You see that? All right. So I solved for that. And then the initial value problem, let's say my initial value problem was that y of 0 equals, what's a good initial value problem for this one? Why not 3? No, let's do 1. Y of 0 is 1. So if y of 0 is 1, that means that 1 equals c times e to the 0 is just 1 minus 1 half, so c equals 3 halves. So my equation is y equals 3 halves e to the 2t minus 1 half. Okay, now I use the fact that I happen to already know the solution to get the capital L and capital M for this theorem. If you were in a situation where you didn't know, where you were, when you're actually probably wanting to know the error bound, you could find L and M using some numerical methods that we're not going to go into right now. So L is the maximum slope on my interval. So let's see, with your interval for number 7 is 0 to 2. Let's say our interval is from 0 to 3. Okay, so L is going to be no bigger than the maximum value of the derivative. So you can kind of look at this guy and say, well, y prime equals 3 e to the 2t. And so the biggest value that gets is when t is 3. So L equals 3 times e to the 6. And then M, let's find M. Well, y double prime equals 6 e to the 2t. So then M equals 6 times e to the 6. And then that means, and then my h, let's say in your homework you're using h as 0.5. Let's say I'm using h as 0.2. Well, then I just plug all of these things into this theorem right here. That tells me an error bound. So I've got little h, that's my step, big M, that's the bound on the curvature, big L, that's the bound on the slope, times e to the L times my actual value of t minus the beginning point a. So in this case, that'd be 0 minus 1. And so you can put that into your spreadsheet as you're computing values. So let's see. Let's see, let's make a new sheet. We'll call this sheet, rename this one activity 4.1 and make a new sheet. We'll call that sheet example problem. And so then here we'll have x and little y and big Y and y prime and actual error and error bound. Not from them, from theorem. All right. So then my x starts with 0, and my step size is 0.2. Your step size is 0.5. And then I drag it down. Okay. Went too far. There we go. So then y. We're given a thing that we can solve, and my solution was 3/2. So this is my solution times exponential 2 times t minus 1/2. Also, this is t, not x. Come on. All right, and then the similar starts off at 1. And then y prime this is my differential equation. So y prime is 2y plus 1 for my example. 2 times big Y plus 1. Okay, and so then this one I can just drag all the way down. And then this one I can drag, nope, I gotta drag these together because wait, the next Y is equal to the last Y plus H, my H is 0.2, your H is 0.5, times Y prime. And then this can drag down to there, and I can drag both of these together all the way down. Okay, I'm way off by the time I get here, but that's because the slope gets gigantic, and the air-bound theorem is based on both the slope bound, and so if the slope is gigantic, your air-bound will not be very good. And so my actual air is equal to my approximation minus the actual value. So down to negative 371. And my air-bound theorem, so that's equal to H, which is 0.2 for me, 0.5 for you, times M, so times 6 times exponential of 6 divided by 3 times exponential 6. So obviously that simplifies, but I'm just doing it right here. Algebraically, I could simplify the exponential e to the 6 divided by e to the 6 just 1, but we'll just keep it there for now. Times parenthesis exponential of L, which is I found my L to be 3 times exponential of 6 times ti minus the first one. So then ti is this number minus 0. And then that finishes the exponential. And then minus 1. That finishes that parenthesis. Okay. So here, oh, okay. It's not very good. That's gigantic. Probably because I have a function with a gigantic slope. So, wow, that's awful. So it's not a very good bound. Or at least I'm doing something, unless I'm doing something wrong. I don't think I'm doing anything wrong. It's just that e to the power of something gigantic will be something gigantic. That's the problem. Yep. Okay, so that's how you would do question question 7. All right, or that's an example similar to question 7. So good luck.